Everyone, what's up? Welcome back to my tutorial channel. Daniel's here and today I'm going to continue on topic 8, hypothesis testing, and I'm going to show you how to perform a z-test. To perform a z-test, we need to know first when do we use a z-test. And there are two testing methods to perform a z-test: the critical value method and the p-value method. Also in this video, I'm going to show you some related results. So first, when to use a z-test. Let's look at this situation. Does coaching improve SAT scores? The College Board reported that the mean SAT score in the recent years was 515, with a standard deviation of 116. Results from an earlier study suggest that college students should have a mean SAT score of approximately 530. A teacher who runs an online coaching program thinks that the students coached by his method have a higher mean score than this. So this is a situation where a teacher make a statement about the population mean. He said he believes the student coached by his methods have a higher mean score. The mean score is the population mean. So the purpose of hypothesis testing is just to verify a statement about a parameter of a population. And here the parameter is the mean, the population mean. So the z-test is one of the methods to test the parameter. Here in this case, the parameters we are interested in is the population mean when we know the standard deviation, which is 116. So the z-test is used when we want to test a population mean, when the population standard deviation is known. And usually the z-test is used when the sample size is at least 30 to make sure that the central limit theorem is satisfied. Remember, if the sample size is at least 30, the sample mean will follow normal distribution approximately. So sample size at least 30 is one assumption to use z-test. And to perform a z-test, we have two testing methods: the critical value method and the p-value method. By the way, usually sometimes you might have a situation where we don't have a big sample size. Let's say we might have like a sample size of 10, 20. However, you need to check the information again. If we have the original population was normal, then the assumption of the sample size is at least 30 is not necessary. So let's look at the first method, the critical value method. No matter which method you use to perform a z-test, we need to know the test statistics. Remember, hypothesis testing is a inferential statistics method. So basically, we use a sample to make inferences towards the population. And here we are making inferences about the population mean. So we need to use the sample mean, because the sample mean is the estimate of the population mean. And the test statistics for the z-test is the z-score of the sample mean. And by central limit theorem, when the sample size is at least 30, we know that the sample mean follow normal distribution approximately with mean mu and standard deviation sigma over square of n. So the z-score of the sample mean is z is equal to x bar minus mu over sigma over square of n. So this is the test statistics. And the critical value method, the idea is we should reject the null hypothesis if the value of the test statistics is unusual when we assume that x not to be true. So whenever we do hypothesis testing, we basically assume that the null hypothesis is true, and we will go and find the evidence to against the null hypothesis. If we cannot find enough evidence, we cannot reject the null hypothesis. So the idea of the critical value methods is to verify if the value of the test statistics is unusual. And in this method, we will choose a critical value which forms a boundary between the values that are considered to be unusual and the values are not unusual. So we will end up to have the critical region and the acceptance region. The region that contains the unusual values is called the critical regions, and the region that contains the usual values is called the acceptance region. So if the value of the test statistics falls into the critical regions, we reject X naught. We reject the null hypothesis. That is the idea of the critical value method. If we reject the null hypothesis H naught after choosing a significance level alpha, we say that the result is statistically significant at the alpha level. We also say that the null hypothesis is rejected at the alpha level. So that's the idea. To be more specific, before we perform a hypothesis testing, we need to choose a significance level, and here I'm going to say alpha is the significant level. The critical value depends on whether the alternate hypothesis is left-tailed, right-tailed, or two-tailed. In the last video, I have shown you how to define whether a test is left-tailed, right-tailed, or two-tailed. So I'm not going to show you again in this video. So for left tail, we are working with standard normal distribution. So basically, to define whether the test statistics is unusual or not unusual, we need to have a critical value to separate the region of unusual values and the region of usual values. So here in this case, if we have a left tail, suppose we have a left tail, the left picture is for left tail test. So for left tails, we have we take minus the alpha, this is a negative value, as the critical value. And the area to the left of it is the critical region, and this area is alpha. So if the test statistics falls into the critical regions, we reject the null hypothesis. If the test statistics falls into the acceptance region here, we do not reject the null hypothesis. Similarly for the right-tailed. The right-tailed we also define a critical value, and for right-tailed it is Z alpha. And the area to the right of the Z alpha is the critical region, and the area to the left is the acceptance region. So we see that for the left tail, we choose minus z alpha as the critical value. For the right-tailed, we choose z alpha. And if we have a two-tailed, then we would have two value about it, that is z alpha half and minus z alpha half. So if the test status falls into the two-tailed, we reject the null hypothesis. Otherwise, we do not reject the null hypothesis. So here for left tail, if z is less than minus z alpha, we reject x naught. For right tailed, if z is greater than or equal to z alpha, we reject x naught. For two tail, if z is greater than or equal to z alpha half or z is less than or equal to minus z alpha half, we reject the null hypothesis. It might be hard for you to memorize these stuff. However, just thinking that the value is said to be unusual if it stay away from the center, if it stay away from 0. So for left tail, we take the minus z alpha as a threshold. If the value is unusual, it's gonna be far away from the mean 0 on the negative side. So it should be less than minus z alpha. For the right-tailed, a value is said to be unusual if it's too far away from the center or 0 and is on the right side. So we have the z alpha here, which is a positive value, to separate the acceptation region and the critical region. Critical region is also called the rejection region. And for two-tailed, if the value is far away from the center from both sides, that value is said to be an unusual value. And here, alpha is the significant level. Remember when we learned about unusual event, if the probability of an event is less than 0.05, we said the event is unusual. Here for critical method, suppose alpha is 0.05. If the value is on the left of minus z alpha, suppose we're looking at the left tail test, we see that the probability of the area to the left of minus z alpha is alpha. So if the test status fall into this tail, the left tail, we said is an unusual value. And similar for the right tail and two-tailed. Another way to memorize it is, for the left tail, the critical value is always negative. The right tail, the critical value is always positive. And for the left tail, the critical region is on the left of the critical value. For the right tail, the critical region is on the right of the critical value. For two-tailed, we have two-tailed. Right at the name two-tailed H1, we're gonna have two-tailed. For one-tailed, we have one tail either on the left or on the right. For two-tailed, we're gonna have two critical regions. Those are the two-tailed of the standard normal curve. So that's the idea of the critical method. And to perform a z-test by the critical value methods, we first state a null and the alternate hypothesis to define whether we are dealing with left tail, right tail, or two-tailed. Step 2, we choose a significance level alpha and find the critical values. Step 3, we compute the test status, which is z is equal to x bar minus mu over sigma over square root. Here mu here because we assume that x naught is true, so we are going to use the specified value of x naught as mu. Step 4. Determine whether to reject X0 as follows. If we are dealing with left tail, if the theta is less than or equal to the critical value minus the alpha, we reject X0. That means if the theta is on the left side of the critical value, we reject X0. For right tail, if the theta is on the right side of the critical value, we reject X0. For two-tailed, if we will have two critical values, the negative critical value and the positive critical value. So if the theta is either less than the negative critical value or greater than the positive critical value, we reject X0. If the theta stay in the middle, that means it's usual. So we do not reject X0. Simply, if the theta falls into the rejection region or the critical region, we reject X0. Rejection region here is the critical region. Step 5, we state a conclusion. So that is the so that's how we perform a z-test by the critical value method. The second method is the p-value method. The idea of the p-value method is to measure just how strong the evidence against the null hypothesis is. We compute a quantity called the p-value. The p-value is the probability that a number drawn from the distribution of the simple mean would be as extreme as or more extreme than our observed value of the simple mean. The more extreme the value, the stronger is the evidence against the null hypothesis. The p-value is the probability, assuming that the null hypothesis is true, of observing a value for the theta that is as extreme as or more extreme than the value actually observed. The smaller the p-value, the stronger the evidence against the null hypothesis. So here, if we consider the left tail, this is the theta z. Even though the picture looks similar to the critical value methods, but don't be confused. For critical value methods, the value here is z alpha minus z alpha. But for p-value methods, we use the theta. So for the p-value methods, we also sketch off the normal, the standard normal curve, and mark the value of the theta. So the p-value of the left tail is just the area to the left of the theta. For right tail, the p-value is the area to the right of the theta. And for two tail, if we have a theta, we consider the sign. If it's negative, we have is positive. So suppose we have a theta of 2.34. So on the normal standard, the standard normal curve, we mark two value, minus 2.34 and 2.34. And the p-value is the total areas of the two tails. So it should be the area to the left of the negative value and the area to the right of the positive value. And because the standard normal curve is symmetric, so these two tail areas are equal. So we basically can have 2 times the right tail area or 2 times the left tail area for the p-value. So to perform a p-value methods, the purpose of a hypothesis test is to determine how plausible the null hypothesis is. We basically begin a hypothesis test by assuming the null hypothesis is true. If the data provide strong evidence against the null hypothesis, we reject this and believe the alternate hypothesis. If there is sufficient evidence to reject the null hypothesis, we conclude that the alternate hypothesis is true. If there is not sufficient evidence to reject the null hypothesis, we conclude that the null hypothesis might be true, we never say the null hypothesis is true. We just say it might be true. And to perform a p-value method, the first step, we state the null and the alternate hypothesis. Step 2, if making a decision, we have to choose a significance level alpha. So for any test, for any methods, we have to state the null, the alternate hypothesis, we have to choose a significance alpha level, and we have to compute a test status. So no matter we use p-value method or critical value methods, the first three steps are the same. Then for p-value method, step 4, we have to compute the p-value of the test status. Depending on what test we are dealing with, if we have a left tail, the p-value is the area to the left of the test status. The right tail is the area, the p-value is the area to the right of the test status under the standard normal curve. And for two-tail, the p-value is the area to the left of the negative absolute value of z, and the area to the right of the absolute value of z. So it's basically 2 times the area to the right of the absolute value of the test status, or 2 times the area to the left of the minus absolute value of the test status. And step 5, if the p-value is less than alpha, we reject at naught. So that is the idea of the p-value method. Many times, some students will be confused between p-value method and the critical value method. So let's look at this example, and I'm going to show you how to perform a z-test using both the critical methods, the critical value method, and the p-value method to see the difference. So example 1, the National Health and Nutrition Examination Surveys are designed to assess the health and nutritional status of adults and children in the United States. According to a recent survey, the mean height of adult men in the United States is 69.7 inches, with a standard deviation of 3 inches. A sociologist believes that the taller men may be more likely to be promoted to position of leadership. So the mean height of male business executives may be greater than the mean height of the entire male population. A simple random sample of 100 male business executives has a mean height of 69.9 inches. Assume that the standard deviation of the male executive height is sigma is equal to 30 inches. Can we conclude that male business executives are taller on the average than the general male population at the alpha 0.05 levels? Whenever you perform a test, I suggest you to summarize the question into notation so that you can recognize the test easier, because if you read a bunch of words here, you might be lost. So here I highlight the important figures. The first value is the population mean, which is 69.7, because that according to a recent survey, the mean height of adult men in the United States is 69.7 inches. So that is usually if you have a historic value, the historic value should represent for the population. This is the value from a recent survey, it's not from the symbol. So that is the population mean, with a standard deviation of 3 inches. So 3 is the population standard deviation. Then a sociologist take a sample of 100 male business executives. So this is the sample. The sample size n is equal to 100. And from the sample we have a mean height of 69.9. This value 69.9 is the symbol mean. So we have x bar is 69.9. And for the null hypothesis, we have mu is equal to 69.7. And actually 69.7 is the published mean from the old survey. And we are working with the population mean with of the recent of the new value. So actually here 69.7 is mu naught, but because when we performing a test, we assume that the null hypothesis is true, and we find evidence to either against it or support it. So here we say mu is equal to 69.7, or actually the same mu naught. So the null hypothesis say that the mean height of the male business executives should be the same as 69.7, and the alternative say that it should be higher, because here the sociologists believe that taller men may be more likely to be promoted to a position of leadership, so the mean height of the male business executive may be greater than the mean height of the entire male population. So the alternative is mu is greater than 69.7. This is a right tail test, and we choose alpha level 0.05. So that's how we summarize the problems. Now we have all the numbers set up, so let's perform the test. No matter which method you use, you have to compute the test status, and the test status here is z equal to x bar minus mu over sigma over square root of n, which is 0.67. So we have finished the first three steps. The first step is state a null hypothesis. The second step is choose alpha level, and the third step, the third step is to compute the test statistics. Now, depending on which methods you use, you will have different steps. For critical value methods, we have to find a critical value. So, because we are dealing with right tail, so the critical value should be a positive value, and it is z of alpha, which is z of 0.05, because we want to have alpha area on the right tail. So the threshold should be z 0.05, because the area to the right of z 0.05 is 0.05. And use either A2 table or technology. We have z of 0.05 is 1.64. And again, because we are working with the right tail alternate hypothesis, so the critical region is the area to the right of the critical values, which is from 1.64 to infinity. So let's look at this picture. We're working with a right tail test. So we have a right tail, and the threshold is z alpha, which is a positive value. The area to the right of this z alpha is alpha, and this area is the critical region. So see that the blue area is the critical region, and the area that is not shaded is the exception region. So if the test status falls into this shaded area, the critical region, we reject the null hypothesis. And here we have the test status 0.67. Z alpha here is 1.64. We see that 0.67 is less than 1.64. So the test status does not fall into the critical region. So we have 0.67 does not belong to 1.64 to infinity. The test status is not in the shaded area here. So we do not reject the null hypothesis. I repeat, we reject the null hypothesis, if the test statistic falls into the critical region. The critical region is the rejection region. And here the test statistic does not fall into the critical region, so we do not reject the null hypothesis. And that's how we perform the z-test using the critical value method. By the p-value method, we are dealing with a right-tail test, so we have to compute the p-value, which is the area to the right of the test statistics. So we see here, the test statistics here is 0.67. We are working with the right-tail test, so it should be the area to the right of the test statistics. And we can use either A2 table or technologies to find the area. So this area is 0.2514. Remember, when you use A2 table gives you the area to the left of a z-score. So to use A2 table, you have to convert the problem from the right-tail problem to the left-tail problems. So probability that z is greater than 0.67 is 1 minus probability that z less than or equal to 0.67. Then we use A2 table to find the area to the left of 0.67, which is 0.7486, and the area to the right of it is to the right of z alpha is 0.2514. Then the next step, we compare with the confidence level. We see that the p-value here is 0.2514, which is greater than 0.05. So we do not reject x0. We reject x0 if the p-value is sufficiently small. Sufficiently small. So now we make conclusion. Because we do not have enough evidence to reject x0. So x0 might be true. There's not enough evidence to conclude that the male executive have a greater mean height than adult males in general. The mean height of male executive may be the same as the mean height of adult males in general. You see that, like, we don't have enough evidence to reject the null hypothesis. The null hypothesis say that mu is equal to 69.7. That means the mean height of male executive may be the same as the mean height of adult males in general. So x0 might be true. So that is an example of right-tail test. Now let's look at a two-tail example. Example 2. At a large company, the attitudes of workers are regularly measured with a standardized test. The scores on the test range from 0 to 100, with higher scores indicating greater satisfaction with their jobs. The mean score over all of the company's employees was 74, with standard deviation of 8. Some time ago, the company adopted a policy of telecommuting. Under the policy, workers could spend 1 day per week working from home after the policy had been in place for some time. A random sample of 80 workers was given the test to determine whether the mean level of satisfaction had changed. Since the policy was put into effect, the sample mean was 76. Assume that the standard deviation is still sigma is equal to 8. Can we conclude that the mean level of satisfaction is different since the policy changed at the alpha is 0.05 level? So before we run the test, we need to summarize the test using notation so that we can recognize the type of the problems. Here, the mean score over all of the company's employees was 74. This is the population mean. With a standard deviation of 8, this is the population standard deviation. And we have a sample of 80 workers, so the sample size is 80. And from the sample, we have a sample mean of 76, so x bar is 76. And we want to see whether the mean level of satisfaction has changed. There are two possibilities. The first possibility is the mean level of satisfaction has not been changed. That means mu is equal to 74. And the second possibility is the mean level of satisfaction has changed. So mu is not equal to 74. So here we test on both sides of 74. This is two-tailed. And the alpha level is given as 0.05. So that's how we summarize the problem. Now, no matter which methods you use, critical value methods or p-value methods, you have to compute the test statistics. And the test statistics here is equal to 76 minus 74 over 8 over square of 80, which is 2.24. This is the test statistics. So by the critical value method, we are dealing with a two-tailed test. So we would have two critical values because we want to have two tails under the standard normal curve. It tells the area is 0.05. So we have the positive critical value is 0.025 and the negative critical value is minus 0.025. So the two critical values are 1.96 and negative 1.96. The critical region is the area that stays away from the center, so it should be on the left of the negative value and the area to the right of the positive value. So we have negative infinity to negative 1.96 and 1.96 to infinity. And we see that 2.24 here, the test statistics, fall into the right critical region because 2.24 is greater than 1.96. So we see that the test statistics here falls into the critical region. So we reject the null hypothesis. And for p-value method, we find the p-value by first we sketch off the standard normal curve. The test statistics here is 2.24, and because we are working with two tails, so we have to have two tails on the picture. So then we have to mark the negative value of 2.24. We have minus 2.24. So the critical, we see that, I'm sorry, for p-value methods, we're not talking about the critical region. So for p-value method, the p-value is the area of the two tails. And because this standard normal curve is symmetric, so you can either find the area to the right of 2.24 and then multiply by 2, or we find the area to the left of minus 2.24 and times 2, multiply the answer with 2. So we see that the left tail area is 0.0125, the right tail area is 0.0125. So the total area of the rejection region, the total area of these two tails is 0.025. So the p-value is 0.05. So the p-value is 0.025, which is less than 0.05. So we reject the null hypothesis. So conclusion, there is sufficient evidence to state that the mean score among employees had changed since the adoption of telecommuting. We see it because there is sufficient evidence to reject the null hypothesis. That means the null is wrong and the alternate is true. So the mean score among employees had changed. So that is how we perform a z-test to verify a scientific statement. There are some related results. The first result is the relationship between hypothesis test and confidence intervals. So another method to run the test is to use confidence intervals if the confidence interval is given. But confidence intervals is only used when we are dealing with two-tailed tests. For one-tailed test, confidence intervals, we have to use different confidence interval. There is one-side confidence interval, which is not covered in this course. So if we test the null hypothesis mu is equal to mu naught versus x1 mu is not equal to mu naught, then if the 1 minus alpha confidence interval contains the specified value mu naught, then x naught will not be rejected at alpha level. That means mu naught is a usual and unusual value. If the 1 minus alpha confidence interval does not contain mu naught, then the null hypothesis will be rejected because the specified value mu naught is an unusual value. Result 2, the relationship between alpha and the probability of an error. When a test is performed with a significant level alpha, the probability of type 1 error is alpha. Remember, type 1 error is the probability that we reject the null hypothesis when it is true. And for z-test, for the test, we assume that the null hypothesis is true, and we find evidence to either reject or support the null hypothesis. So if we reject the null hypothesis, we basically reject it when x naught is true, and that is basically the probability of type 1 error. So alpha is the probability of type 1 error. And the smaller the alpha value we choose for the significant level, the smaller the probability of type 1 error becomes, because the probability of type 1 error is alpha. And the larger the probability of type 2 errors becomes. Type 2 error is we accept the null hypothesis when it is completely wrong. So that's everything for today. Thank you so much for watching my video. I hope you guys find my video helpful, and see you next time. Bye.